For problem 13, what we are doing is trying to find the critical numbers of some functions. This first guy is more difficult than anything that I would have you do on the test, but I think it's worth just being able to go through these steps and seeing how to find critical numbers. So first of all, let's remember that a critical number is any place where the derivative of a function is either equal to 0 or is undefined. Really specifically, we only care about those places where the derivative is undefined, but the original function is actually defined. Because critical numbers, we're trying to find places where we have a maximum or minimum. And we can't talk about a maximum or minimum of a function at a place where the function isn't defined, because if it's not taking on a value at a particular value of x, it can't have a maximum or minimum there. Alright, so let's take the derivative of this guy and then we will set it equal to 0 and solve, and also we will figure out where it's undefined. So this is the product rule. X to the 2/5. To evaluate the derivative of that, I apply the power rule, so I get 2/5 times x to the minus 3/5, and I leave x plus 7 alone. Then I add x to the 2/5, and I take the derivative of x plus 7, which is just 1. And I want to do two things with this. I want to set it equal to 0 and solve, and I would also like to figure out where this is undefined. It's actually not too difficult to just look at this and figure out where it's undefined. I have to say, where do I run into any issues plugging in a value of x into this expression and possibly, and getting something that doesn't make sense? So when is x prime of x undefined? Well, let's see. X to the 2/5. That is defined for every single real number, because this really means take the fifth root of x and then square it. Every real number has a fifth root, and I can square any real number, so this is defined everywhere. Over here, what is the issue? X plus 7 is defined for every real number. X to the minus 3/5 is not defined for every real number, because x to the minus 3/5 really means 1 over x to the 3/5. So I have to worry about dividing by 0. And when is this denominator equal to 0? When x is equal to 0. So when x is equal to 0, this doesn't make sense. And so this expression doesn't make sense when x is equal to 0. If x is not 0, this makes sense. And I can plug it into x to the minus 3/5, multiply by x plus 7, multiply by 2/5, add to x to the 2/5, and I'm fine. So the only place where x is undefined is x equal to 0. And again, going back to what I was saying just before, I can plug in x equal to 0 into the original function, because 0 plus 7 is 7, 0 to the 2/5 is 0, 0 times 7 is 0, great, that makes sense. So x equal to 0 is a critical number. Now the other question is, when is f prime of x equal to 0? And this is going to be a little bit more work. What I really need to do is, I'm going to set this equal to 0 and try to solve it. There are a couple of ways to try to do this. So let me delete this, and I'll rewrite what f prime of x was equal to. And f prime of x was equal to 2/5 x to the minus 3/5 times x plus 7 plus x to the 2/5 times 1, so that's just x to the 2/5. And I'm setting this equal to 0, and I'm trying to solve it. How can I solve this? Well, one way of trying to solve this is to try to, first of all, get rid of this x to the minus 3/5. That guy is kind of annoying. And so a way that I can get rid of the x to the 3/5, let me get a big eraser here. Okay. One way to try to solve that is to multiply both sides by x to the 3/5. Why x to the 3/5? Because x to the 3/5 times x to the minus 3/5 is equal to 1. I'll write that over here. X to the 3/5 times x times x to the minus 3/5 is equal to, when I multiply, I add the exponents, 3/5 minus 3/5. And 3/5 minus 3/5 is 0, and x to the 0 is equal to 1. And implicitly here, I'm assuming that x is not equal to 0. If x were equal to 0, this step just would not make sense in the first place because x to the minus 3/5 is not defined when x is 0. So when I multiply out, this x to the 3/5 and this x to the 3/5 cancel when I distribute. So I get 2/5 times x plus 7 plus, over here, x to the 3/5 times x to the 2/5. Again, I'm distributing. X to the 3/5 times x to the 2/5. I add the exponents. X to the 3/5 plus x to the 2/5 is x to the first power. And the first power of x is just x. So this is equal to 0. Great. Why don't I also multiply both sides by 5 to get rid of this denominator of 5 over here? Oh, and on the right-hand side, 0 times x to the 3/5 is 0. Okay. So 5 times 2/5 is just 2. So I get 2 times x plus 7. 5 times x is 5x. And 5 times 0 is 0. And then I distribute again. 2x plus 14 plus 5x is equal to 0, which tells me that 7x plus 14 is equal to 0. And I leave it to you to show that this means that x is equal to negative 2. Great. Okay. Just for kicks and just because this sort of thing seems to be difficult for a number of us, I'm going to do this a slightly different way. I will again take our expression 2/5 x to the minus 3/5 times x plus 7 plus x to the 2/5 and set that equal to 0. Now another way I can attack this is trying to start to unpack what this means. X to the minus 3/5 really means 1 over x to the 3/5. So I can rewrite this expression as 2 over 5 times x to the 3/5 times x. You know, screw it. I'm just going to do this. 2 times x plus 7 over 5 times x to the 3/5. So 2 and x plus 7 are in the numerator. 5 is in the denominator, and I'm going to put x to the minus 3/5 into the denominator by making the minus exponent positive. And then I'm going to add x to the 2/5 and set this equal to 0, or it's equal to 0. Now, I would like to add these two guys together. To solve this expression, I really need to, one way of attacking it anyways is to add these two expressions together. And to do that, I need to get a common denominator. Well, the only denominator in sight is 5 over 3x, or 5 over x to the 3/5. So multiply top and bottom of x to the 2/5 by 5x to the 3/5. If you ask where is the bottom of x to the 2/5, it's implicitly over 1. Okay, so 2 times x plus 7 over 5x to the 3/5 plus x to the 2/5 times x to the 3/5 is x to the 1, as we've already seen. So we get 5x over 5x to the 3/5 equal to 0. And then adding numerators, I'm going to distribute here too. That's 2x plus 14. So 2x plus 14 plus 5x gives me 7x plus 14 over 5x to the 3/5 equal to 0. Great. And then if a over b is equal to 0, then a is equal to 0. So 7x plus 14 is equal to 0. Solve. We already solved this. X is equal to negative 2. Great. Also note that this expression is nice because it shows you literally when this expression can't be evaluated, when the denominator is 0, which happens when x is 0. Great. So this is another way of doing it. I'll even show you one more thing. Let me just erase, undo a million steps here. and show you one other way of doing this. At the end of the day, all of these things are really equivalent. I'm just sort of doing different steps at different moments in time and whatever. Another thing I could do is subtract x to the 2/5 from both sides. And I get 2/5 x to the minus 3/5 times x plus 7 equal to minus x to the 2/5. And then I could say I've got a power of x over here. Let me divide both sides by this power of x. X to the minus 3/5, x to the minus 3/5. And dividing by x to the minus 3/5 is the same thing as multiplying by x to the 3/5. So I end up with 2/5 times x plus 7 is equal to, again, x to the 2/5 times x to the 3/5 is just x to the 1, which is x. I get this, blah, 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 blah. You go ahead and you get the same exact thing. I mean, it looks a little different this time. I suppose if you multiply out and multiply both sides by 5, you get 2x plus 14 is equal to negative 5x. But again, this tells you that x is equal to 2. At the end of the day, all this stuff is the same. At some point, I'm multiplying x to the 2/5 by x to the 3/5. In what context am I doing it? I don't know. But it's either in getting a common denominator, or it's trying to get rid of this x to the minus 3/5, or it's trying to get all the just plain old x's to one side. But it doesn't matter. It's all accomplishing the same thing. And at the end of the day, I get x equal to 2. It's worth it to be really fluent in your algebra to attack these sorts of things. It's just, yeah. So anyways, that's what's up.